Thank you. I hope I will calm down soon so I'm able actually to operate. So let's try. So first of all, we will have a short history lesson about the platform processors and the history of the platform processors. Then, obviously, we will have a look how it looks today. And most of the lecture we will spend together doing the hardware and the firmware analysis of the system management unit. And so x86 processor, as you might know, it is quite old processor from late 70s. And what is interesting is that this processor always had little small processors which were helping this big processor. It is really quite old time from 1984 and also 1983. Those processors were the platform processors without possibility to change the firmware, but they handled important functions, which in that time was a keyboard and also the resetting the whole platform and the famous A20 hardware. I want to just to make sure what is the level here. So who knows what is A20? Yeah, great. I'm at the Hackers Conference, so it's okay. Yes, and so those were the first processors. And as you might know, the laptops generally also include one more processor, which is usually used for the firmware management and hot plugging events and special keys and so on. And this controller has usually 8051 CPU or some super Hitachi CPUs and so on. So this x86 platform currently is using such things. And if we look how it looks in today, that we will find that the border between the hardware and software somehow diminishes a little, and that there is a lot of firmware present. If you look to the Linux kernel, which has this firmware directory or the package, you will immediately spot that virtually any peripheral today has a kind of firmware which needs to be uploaded and to operate. But in our lecture, I would like to concentrate on the platform processors which are helping the main processor, and let's start with the Intel processor. As you might know, there is one which is remarkable. It's an Intel management engine. Who knows this one? Yeah, great. So let's go. Let's go to the AMD because maybe it's not so many known. So in AMD platform, which you can buy today, you will find several other processors. The first one which I listed is the system management unit, which will be more on that later today. Then there is even a small 8051, which is located in the Southbridge, which is called integrated microcontroller. And of course, there is also some other controller in the USB, which you can figure out in your homework what kind of control it is. And in the end, the very recent AMD processors comes with something which is called platform security processor. And this processor is ARM Cortex-A5 with a trust zone thing. And the reason why AMD introduced this processor is to redo the chain of, or the root of the trust. So the idea perhaps behind this is to have something else which gives the root of the trust while booting the x86 processor. So in fact, something which verifies the BIOS before even the BIOS is started. But in this lecture, as I said, we will concentrate on the system management unit. But x86 is not the only platform which has such kind of special platform processors. If you look to ARM or PowerPC, you will notice that there are special channel or DMA processors which are also running their firmware. And here is just a funny table. I hope I have it correct. So I'm not aware if there is any malware running on this kind of platform processors, but as for today, I can put the platform processor has some bugs. So let's have a look. And to finish my introduction, I think it's a good way to increase kind of awareness of this, and because these platform firmwares are in every modern platform, and you cannot simply disable it because it's a part, it's a genuine part of the system. So you have to live with it, and there could be possible security problems. And this is, I think, very important point, that the hardware engineers are involved, which means most of them are not the software engineers. So if you ever have looked to some BIOS assembly codes or some small embedded system platforms, you know how clumsy they are, and this doesn't help the security much. And there is kind of advent of some very special firmwares which are found which can be loaded to the current platforms. Most likely you are aware of the bad USB stuff, which I think I have it. It's not in fact in the USB 3.0 controller, but in the client in the USB device. But what you can also run is that you can run your Linux in your hard drive, because somebody with the Sprite TM name found out that the hard drive PCB contains 3 ARM processors, and you can run MMU-less Linux inside your hard drive, and also fix the etc shadow if necessary, for example. So as you can see, now we live in the age where those processors are somehow bubbling out, and something needs to be done. Yes, and I was speaking about the open source firmwares, and I believe there are also perhaps some closed source firmware, and here you can choose your right permutation of the vendor. Okay, so this was just a first part of my story, and the second part is about how I went through the SMU stuff. And as usual, it begins that people read books, and some reads also data sheets. And if you do that and have a look to this document, which is very nice, it describes most of the stuff, how the modern AMD processor is working. It's called AMD BIOS and Developer's Guide. And if you have a look into this document for the very recent families, you will find there this quote that there is something which is called the system management unit, and it takes responsibility for the power management and system-related tasks. And the last sentence is quite nice. It says the SMU contains a microcontroller to assist. And this is the point where I started to think, let's have a look what is it, and if I can get some fun of it. So, and because I like the stuff like ciphers and so it was very ideal topic for me. And this thing is also very special because it lives in Northbridge, and Northbridge is the part of the system of chip. And it means in the end that it lives in the CPU. And this was the reason why I put the name Matroshka processor. And while I was preparing my lecture, then I noticed that the Western people are not, they simply don't know what the Matroshka is. And so I brought one to show you. So this is the main CPU, and if you open it, there is a smaller one. And but please, this is not a part of the Czech culture, because we were the Soviet satellite some 20 years ago, And there were not other presents available, so we kind of have still some of them hidden in our homes. But please do not buy them in Prague as a tourist souvenir, because it's a tourist trap, and please don't do that in the end. Okay, so now back to our lecture. So what kind of microcontroller is there? Of course, nowadays, the Google knows quite a lot of answers, and if you put this to the Google, you will get some more data sheets, which we will need later, but also you will get something from LinkedIn, and not just this one, but also a lot of other pages which describes a lot about what the SMU is in fact doing. So here I won't read it at whole, but in fact, as you can see, it is lattice LM32 processor. It's doing some dynamic power stuff, and this guy apparently implemented the adaptive algorithm to deal with the power management. But please don't blame this one, because there is many more on LinkedIn, especially for the AMD employees and other employees. Okay, so if you know that this is latest Micro LM32, then here is a quite short introduction. So it is, let's say, open core processor. You can get SDK for it, or you can download, or you can compile your own toolchain, and you can get also the reference manual. So this is, in general, a very good start to think about this. And the LM32 processor really likes the number 32, because it's a 32-bit processor with 32-bit instruction size, and you can guess how many registers inside processor it has. Yes, it's 32. And because in the next part of the lecture, I will need this information, so just quickly, we have the R0, which should hold the 0, and the rest is quite obvious. This architecture is not like x86. It uses link register to save the return address from the function. Yes, and so far we know what kind of architecture we have, but we don't know where to look for the firmware. So the hard way is, of course, to desolder the flash or the flash chip, which is on the main board, read it out in some programmer, and look if there is not the firmware. But in fact, there is an easy way, because on these platforms, the BIOS image is a complete image of the flash. So you can have a look for the firmware in this image, so you don't need to do the soldering stuff and reading out. And I put some clue here that the firmware is part of something which is called AGESA. This is AMD platform initialization blob, which initializes the every aspect of the AMD platform, and this is included from AMD into the vendor BIOS, and it is called during the BIOS execution to perform the initialization steps. And to get the firmware, you can download virtually any BIOS from the net. For example, for the FM2 motherboard, which I was using for my experiments. And now, because I already told you it's in the BIOS image, so you can try the text search, and the search is for the SMU. And if you do that, you will find something like this. If you look to the slide, there is _SMU, _SMU, and this thing is most likely just an anchor to allow other, perhaps AMD people, to find it more easily inside the blob. I have no other explanation of this. Then the bold text is actual firmware, which is for the SMU part. And you have many firmwares, or many, not many, like 3 or 4 in the AGESA, because One, it just supports different CPUs like Trinity or Richland, and also others like Arizo, for example. So the next thing is that we are on the communication congress, so we have to communicate also with this processor. And we would like to communicate from the x86 processor. And this is where the document I mentioned is again helping, because it is described and documented in the public documentation that there is these two registers which you can use as kind of gateway to this address space of this processor. And here, let me take a little detour that if it is not documented, it doesn't mean it doesn't exist, it's just a delay. And on the other hand, I do appreciate that AMD is putting a lot of effort to have documented platforms way more than the Intel, so please try to support them at least like this. So let's write some simple utility to dump the address space of the system management unit from running system. I use the Linux. So if you do that, I know it's rather small, but well, I will fix it later. If you do that, you will see that it's kind of strange data. It's repeating 55, 55, AA, and again, and this is for the first 64 kilobytes. So then it's getting a little bit better, because you will immediately see that at the offset of 64 kilobyte, it starts to be the same as you have found already in the BIOS image I analyzed. But what is strange is that after the 256 bytes, there is again this 55, 55 AA, which means that the runtime firmware is most likely hidden from you, so you cannot modify it, and then some random garbage follows. So this is how it looks if you dump first two 64 kilobyte segments. I put it into the nice table, so it is more easily understandable. We will look now to the header, and then we go back to the firmware. Okay, and I need to drink some water because. Okay. So this is quite easy stuff. In the firmware header, you will find what you think it should be there. You will find out that there is a version number, there is a length of the header, there is a length of the firmware. There is also something which looks like entry point at the offset C, and then at the offset 10 in hexadecimal, there is something which looks like a checksum. It looks like very random data. And in the end of the header, there is 55AA, 55AA signature. And then it continues with some firmware, which we don't know yet. It could be the first instruction. So let's have a look at the instruction stuff. So as I said, it immediately follows the header. And if you disassemble this instruction, this 000, like 3 zeros and 98 at the end, and the second one is the same, so you will get this instruction, which is quite unhappy, and it is garbage. But you have to try something else, and it's like big endian, for example. And if you do that, you will get something which is very promising, because as I have shown you, it is expected that in register R0 is in fact a 0. So it looks good. And is there someone which can do something with the radar software? Yes, please, I will need some kickstart to this, because as you will see, I did it in very own way. So I decided I will convert the firmware to the ELF file, and I did it with the object copy like this. So I created one section which I marked that it's executable, and then I used object dump to dump it back. And if I have done it, so I get these first steps. So here, as you can see, it's just zeros. I don't know why twice time, but it is so. The R0, then it disables interrupts and sets up the exception handlers. And then it sets in other place in the routine, set up the stacks and zeros the BSS and its classic CRT0 startup. So I decided I will put back some more symbols so I can use nicer object dump. And exception handlers were described in the LM32 manual, so I could add more data to my linker script and identify the exception handlers of the firmware. And if you look to the functions, they look pretty standard. They have some prologues and epilogues. I just skip this for now. And here I think it was a great idea. And I said that let is the SDK, and I looked into the SDK and found out there is CRT0 RAM S and some C functions which were handling the interrupts and interrupts routines allocation and registration and so on. And I also checked the binary image of the example which let is included in the SDK, and I found out that AMD in fact uses this also. So I was able to fill my linker script again with some more functions. It's not exactly the same because of the different GCC most likely, but it's very similar. Okay, so let's see how to communicate with the firmware from the operating system or from the BIOS. You can read in the manual that it is possible to invoke something which is called SMU firmware request. And this is documented again. And you will just write some request number to a doorbell register. Then you will just trigger the interrupt inside the doorbell register. And the SMU will get the interrupt and proceed with this kind of interrupt, and then also return if the interrupt was or this routine was successful or not. So in the detail, this is what I found out, is that most of the stuff is power management related. It's something which is called budget-aware power management, and that the custom registers are usually located at the end of the second 64 kilobyte segment. And this is not only this, there were also some functions or some service functions which were quite easy to understand. There were some for the flashing of the data caches and instruction cache. There was also a very special request which I nicknamed ping request, because it just incremented by one some register, and this was all what it was in fact doing. So now we know quite a lot about this SMU, and now we need to ask some questions. So if it is possible to run some program, our own program on it, and what are the problems? So the obvious problems could be that there is this protection thing, which means that the code is protected from the runtime modification. Plus, there is something which looks like the checksum. Plus, if we would modify the BIOS, it would mean that the BIOS on its own has some kind of checksums. So this is the problem we need somehow to solve. So this is again just from the firmware header, as I was telling in the beginning. There is this 20 bytes of something which we'll need to find out. And this 20 bytes is in fact 160 bits. So what this could be? Yes, it could be SHA1. So I tried really hard with many permutations, like compute it from the firmware without the header, with the header a little bit in the end, with zeros instead of the places where it is, and I simply failed. I didn't find out how to do that. Yes, and this is what I said already. So the second thing is runtime code injection. So how to do that? We have this problem that the code and data segment is hidden, and it looks like it's protected. So, but there are also ranges which are not protected, and this was seen in the big dump I showed you in the beginning. And let's examine this further and see if we can write there something. So in this slide, you see that there is this 5.5 and so on again, and at the offset DC 50, it stops, and there is some random stuff. And the header, as I have told you already, is also visible. So these are these two regions, and in the end of the 64 kilobyte segment, there is this communication area with some random garbage. So if you look to the offset data, which are to be seen right after the protection ends, it looks like something like this, and there is some strange things happening here. So the offset data matches some functions in the firmware, which I need to tell you what is it. So I don't know. And what is more strange is that this part is still part of the BIOS image. So somehow something went wrong with that, even more than terribly. So there is a first problem that there is some problem that the 256 bytes is missing in the protection, and the header is also the same length, so it looks like it's kind of a problem that this part is not covered because someone forgot it to add it over there. So because of this, we need to ask more, can we change this offset data during runtime? And the answer is yes. And is there something which invokes this function pointer from the offset data? And the answer is also yes. In fact, there is IRC, there is this dispatcher which handles various interrupt requests from the SMU, and one of the request is also, which is present there, this SMU request function handler, which gets invoked. So now we can think about how to run the program. So I took the obvious approach to load it to unused part of the second 64 kilobyte segment. I've put there the quotes because I don't know if it was a really unused place or I was just lucky. So we can modify the pointer in the offset data, and then when finished, we return the control to the original function to handle the request and also the IRQ request, so it's cleanly done. And while at it, I also included here, this is actually the function which is invoked for the SMU request. And now we can also go through this one. So first, it acknowledges this SMU request interrupt, which came because of this doorbell register. It loads the request number, which was stored in some other register, then it masks it and shifts it, and then it loads the base of the function pointer table, which is different from previous. This is another function, and load it to the register R2, and then call it. So is here anyone who sees already the problem? No? Okay. So I give you more time. Okay, so there is no check for the bounds. So in fact, it means that you can run something which is not in the the array for the pointers. And this is bad. So something went wrong again. Because we control this 15 bits value which we are passing to the request to this function, then the offsets where the pointer's table starts is also known. So we can simply load to some address a pointer to our function which we can load there. And if we call the SMU requests with the right number which matches, then we can again execute our own code. Yes, including our injected functions. Yes. So in this case, it means that we can execute our own code inside the SMU, but there are still some regions which are not available to us, and I was interested what I can find there. So in this case, it is the region for the first 64 kilobytes. Yes. So everything begins like writing a program. So let's start and write some. And this one will be quite easy. We will use the methods I told you right now to actually program some kind of function which allows us to copy 4 bytes from any place inside the firmware and copy it to some place which is not protected, which we can read. And we can use this dumper as many times as we like, and it means we can dump the first 64 kilobytes to see what is there. Yes, so let's have a look what is there. I do think it's most likely a ROM. I like my processor, and I have written data there only once, very covertly, and nothing happened. So most likely this part is a ROM part. What is interesting is that it has the same structure as the runtime firmware, but with more complex initialization. And it implements only SMU request 0, which verifies the firmware which is loaded by the BIOS. So while the computer is starting, most likely this ROM gets executed first, then it waits for this request, and BIOS will load the firmware from the BIOS image to the second 64-bit 64 kilobytes, then invokes this, and the firmware in the ROM will authenticate this kind of firmware. So, and if we can analyze it, we can also see what went wrong with this 256 byte offset, and of course what kind of hash is used. So this function, if you look, it is not one function. In fact, it's much more than one function, and there are some strange constants like this. Anyone knows what these constants are? I didn't know either, so I had to use help. And if you look, there is another clue that it's SH1 or HMAC. And I had now difficulties because I didn't have any proper disassembler, so how to make sense of these big functions. And I found out I can use something which is obviously known. It's called QEMU. So QEMU, it has support for LM32, and I hack it a little bit to have support for this memory layout, which was like trivial change to one file. So I loaded in the QEMU the ROM part firmware and RAM part firmware, and I also started the QEMU to executing the authenticate function. And I was able to debug it with the GDB and to see what's really happening. So now what I have found out is here. So The authenticate function, it loads data from the firmware header. It flashes the data caches, computes the hash function, flashes data caches again, and then it checks if the hash is matching in the firmware header. Here it is using the constant time algorithm, so it means if the hash is different, you cannot use the timing attack as it was possible, I believe, in Nintendo VII or something like this. So far, so good. It sets up also the protection registers. And here is the problem because the size of the firmware doesn't include the header. So they thought it's included, but it was not, and this explains why there is this 256 bytes gap on the part which should be covered, but it is not. And it changes also the reset vector of the LM32. So next time the ROM is not executed anymore, and the authenticated firmware is run. And in the end, it signals back the results to the BIOS. So how it looks with the header checksum. So it is not a checksum, but a hash, and debugging helped, and this is what I was telling last time, and it also means it is a symmetric key, and if it is a symmetric key, if there is anyone with a key, he can or she can sign on firmware. I know that this question will arise, so I will answer it. Wait a second. I do have some keys. Yes, okay. So now you can close your eyes. Yes. Yes, so who has closed the eyes? It's written no, close your eyes, really, I'm watching you. And wait for the next slide. So the slides, now you can open them, so you can actually read that. It's called The Secret. So now I will press the space. Now you can see there was a little spoiler because the 42 is in fact the slide number. So let's move on. The slide number 43, there will be no 43. There will be some joke which will be fun, at least for someone. Is there anyone from Czech Republic? So great. This is not a secret in Czech Republic, and it is not a secret anymore here. So I will also skip it. And the secret, of course, remains a secret. So, but now it is time to write some email to AMD, and we need to write them something. So this is what I have done. I wrote to whom it may concern. I have discovered a security vulnerability in the recent AMD processor which allows arbitrary code execution on the system management unit. And I have a trouble to find out whom to write, so I decided to use LinkedIn to find some contact to some sensible engineers which looked like they are responsible for this. And how to support the claim? I changed the ping function to add, instead of 1, to add 42 in hexadecimal. And I fixed the hash, and then I send it to the AMD. And and now something about how it went. So I analyzed the firmware during the Christmas 2013 while I was watching Chaos Communication Congress in a little window, but in the big window, the firmware. And sometimes later, I found the bugs I presented to you. And I've written to AMD on last days of the April, and in like 2 weeks, I received a response. Please, can you give us more information? And so I started to encrypt the communication between me and AMD. I've written in the detail what is the problem, and then in July they acknowledged the problem. In the meanwhile, there was some communication, and in November, at the end, I received a list of versions which will contain the fix, so now it is fixed. And the conclusion is that they responded like to the next day, and because they are on another continent than me, so it was fun fast to speak with them. And that's it. And yes, the fixed problems, both issues are now fixed. So the firmware is now padded, so there is not a problem again with this problem inside the routine which is authenticating the firmware. The problem with the SMU request function check, it is also fixed, and some other unrelated fix to these vulnerabilities in some other processors that are also fixed. So how it looks. As I already told you, the SMU firmware is part of the AMD AGESA, and now it is time to ask your vendor for updated AGESA, and I think it is a good idea to do that and to support this because it's the vendors which are delivering the BIOS updates to you, not the AMD, and this is perhaps the only way how to force them to update also the older platforms is to simply bug them and ask them for the fixed AGESA, which is here. So in this table, you can see the processor names which are affected by these problems. Also the AGESA version number, which you can get if you search in the BIOS image for AGESA string, then there is this string like begins with 1.1. And the SMU versions, which are listed over here. In my presentation, in the slides, if you go back, then later, I use the version AA, which means 1010. So you see now it's version 1014, which already includes the fix. And I use these, let's say, some nicknames of the processors, but it is easy to find them using Wikipedia. So you will find it, or just ask me or drop me an email if you have some problems with that. So thank you for your attention.
Rudolf agreed to a Q&A session, so please line up on the microphones. Microphone 3.
Yeah, sorry, I thought I need another microphone. I have my own. Yes, I know.
Cool. So two simple questions. First off, what can you actually do from the SMU? Can you read anything from memory? Can you actually do anything else than just respond to interrupts?
Well, it was not a purpose to analyze this for me. I simply took my journey, and I didn't want to damage my processor. I'm not sure if it is even possible to physically damage it. I don't know if there is any DMA available inside this processor. I would bet it's in the USB-free controller, which needs to use DMA. I don't know if this processor uses the DMA. But I forgot to tell you that I have here a guest from AMD, which can most likely help me to answer. Please welcome David.
Hi, David.
Hi, everyone. Yeah, with regard to that specific question, The SMU appears to software as a PCI device, and it has the same capabilities that you would generally expect of a PCI device, which includes DMA. It has, of course, some additional capabilities with regard to its specific function within the SoC regarding power management and things like that, but yes, it is able to read and write memory.
Okay, awesome. So the other thing is, how persistent is firmware once a geezer actually puts anything in? It's basically volatile, right? So if I override like if I'm malicious and I patch the host's firmware, the BIOS blob to have a malicious piece of LM32 code in that blob that I recalculate the checksum for, that I now can, since I do know that all the CPUs allow me to read it out, and the ROM doesn't change since the last time, I can basically just infiltrate any random CPU, can't I?
All right, I guess so your question's about the window of vulnerability, right, between power on and when the firmware is loaded?
Yep.
Yeah, that exists, and that's unfortunately not something that we can really patch in the field. I guess our response to that would be that if you are able to have more trust in your early BIOS code to correctly load that firmware, then that will help address that. And so some of the technologies that we are working on with our newer products include things like hardware validated boot, where we have the reference platform security processor verify the integrity of that first BIOS block that executes so that you can have that chain of trust going forward. But yes, I agree there is a window.
Okay, that makes sense. Thanks.
The IRC has a question.
Yes, thank you. The question is, what is exactly in the SMU? And is there a power management unit also in it? Could it be used to overclock or activate more cores?
Well, I think it is used for the power management stuff, like the dynamic or adaptive power management. I don't know if you can overclock way more, or if you can unlock some other cores. I don't think that David will tell this to us, so I don't know.
Yeah, I would say go and have fun. Let me know what you find.
Okay.
Microphone 4.
Thanks for your talk. Just a quick question. So currently the BIOS, the actual BIOS image pulls that SMU 0 request to verify the BIOS image, right?
Yes.
So you could, in fact, just remove that from the BIOS, assuming you could recompute the BIOS checksum and kind of bypass the whole...
I'm not even sure if the computer can run without that, so... I think you have to load it.
Well, no. I mean bypassing the SMU checksum, not the SMU loading. Or is it? Because if the BIOS started, if the main CPU started first.
I'm sorry, I can't hear you very well.
Sorry, if the main CPU started first, and then it loads the SMU image, and then it calls something to verify the BIOS image was loaded correctly. The BIOS image must have been already loaded, right? Or am I getting it wrong?
So the sequence is that the main CPU x86 starts to run and the SMU in maybe same moment is running also, but it is running the ROM firmware. And when the BIOS is doing its stuff, it will load the image to the RAM of the SMU unit, the second 64 kilobytes, and then it will invoke the authentication function. And unfortunately, I don't know any details what could happen if this is wrong or if you don't do that. So again, maybe David will help.
Yeah, I think I may have created the confusion. So let me try to address that. The statement about verifying the BIOS code, which loads the firmware, is a statement with regard to newer products, starting with the Mullins product that include a platform security processor, where the platform security processor is the first microcontroller that comes up out of reset. For the older parts that do not have that, what Rudolf just said was correct.
Okay, thanks.
Microphone 2.
Okay, you notice that now we should rely on the mainboard vendors to supply BIOS updates containing the patched firmware blobs. from my experience with Intel mainboards, I have very little trust in the mainboard vendors to do proper age macking in their BIOS updates. So do you see any chance in just swapping those blobs in existing BIOS updates? I mean, I know for Intel that it's definitely possible to patch BIOS updates which are not properly secured.
I think you will face the problems with some other BIOS checksums in the end, and I would recommend you to use the core boot, and because core boot has the fix for this problem also.
Yeah, that might work as well. Good point. Thank you.
Microphone 1.
Hi, I was just wondering, I've heard from companies like Facebook, Microsoft and others that they put out pretty huge bounties for security vulnerabilities found. Did AMD reward you for basically doing their job?
No.
I'm buying him dinner. What are you talking about?
I didn't want to sell this because I thought if maybe some other people know about this, so let's make it public to balance out the world, our world. And yes, it cost me some money to get in fact here and speak about you about this, so I'm a little bit at the minus, but I'm enjoying the Congress very much, so it's okay for me.
Good for you. Number 2.
Yes, thank you for your talk. Did AMD actually change the salt they use for the SHA macking?
I think no, it's still the same key.
So basically, if you take the same steps that you did, you can just find the salt and write your own firmware for the...
Yes, in general it is possible, but there might be a ways how to put there the new keys or the new salts.
Yes, but if they would, then these would be supplied in BIOS updates, and you can just extract the new seeds or the new seeds.
Yes, it's a fairly good game. Maybe David can tell something.
Right. So obviously the fix that was released is new firmware, and so if you take that out and you write your own thing that gets loaded before that or something like that, then you're running essentially with the same device that Rudolf did. The key or salt in question is hard-coded into the silicon itself, so it's not something that unfortunately can be changed.
Okay, thanks.
Number 2.
The first part of my question you already answered because it was just that question. So after applying the new firmware, new vulnerabilities notwithstanding, the SMU is then safe.
Yes.
So with this fix, it's okay now because the window is closed. You cannot access the memory anymore, and you cannot load your own code into it anymore. And as long as you have the BIOS blob in the chip, it's okay.
As far as we know, unless you guys find something else, yeah.
Thanks.
And if you do, I'll just say, since Rudolph's encounter where he had trouble finding someone to talk to at our company, we have set up a new email alias that's listed on there. So if you do have time to experiment and you find anything, we'd love to hear about it. So please email us.
So thanks to Rudolf
Thank you
for
very much.
finding this bug and make us all safer.
Thank you.
And for the talk.